6.3, we're proving quadrilaterals are parallelograms. One of the things that you want to notice right off the bat is we're proving quadrilaterals are parallelograms. So we already have to know it's a quadrilateral. If these things aren't quadrilaterals, if you're looking at a figure that is a hexagon, well, it's not going to be a parallelogram. It always has to start off with a quadrilateral. It has to have four sides. So in this case, we're going to be looking at the converses to theorem 6.2 and 6.5 that we looked at in the last section. So the blue parts are going to be put into this blank. So theorem 6.6 says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So it is key about the quadrilateral. Both pairs of opposite sides are congruent, then the quadrilateral is a parallelogram. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So these should all look familiar from the last section. If an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. So these both things are important. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Okay, very important theorems to know. And we can start adding one new one. This is not a converse from the last section, but it says if one pair of opposite sides of a quadrilateral, so it has four sides, are congruent, so if these sides are congruent and parallel, then the quadrilateral is a parallelogram. Okay, so we don't have to know anything about these two sets of opposite sides. So here's our first example. It's probably the hardest type of problem you'll see in 6.3. We're going to show using a coordinate proof that a given figure is a quadrilateral. So we know the vertices are at -1, 2, 3, 2, 1, -2, and -3, -2. Okay, so these were the vertices A, B, C, and D. So I'm going to draw in the sides. And we know this is going to be, it looks like a parallelogram, but that's not showing it. Okay, in order to show it, we're going to use some of those things that we did in some of these theorems. Okay, so we could basically use all these theorems. We can use the distance formula, okay, to show opposite sides are congruent. So theorem 6.6, opposite sides are congruent. So if opposite sides are congruent, we want to show AB congruent to DC and AD congruent to BC. So if we're going to use this theorem, we got to show that. So how do we show that? Well, we can look at, we actually don't have to do much calculation to find the distance of this segment. We get to just count it. 1, 2, 3, 4. AB is 4, and DC is 1, 2, 3, 4. Those ones were pretty easy. And now we can find the length of AD and BC. Find those lengths. Okay, in order to do that, you can use a right triangle and Pythagorean theorem, or you can just use the distance formula. So 2 up 4. I'm going to get rid of that in case we want to do more stuff, but 2 squared plus 4 squared, we have 2 squared is 4 plus 16, 20. But now it's square root of 20. And if you look over here, over 2 up 4, that's going to be the square root of 20 as well. So we showed that this is a parallelogram by theorem 6.6. Now we could also show it by theorem. We could use just about any of those theorems. You could show that the diagonals bisect each other. Find the midpoint of this diagonal and the midpoint of that diagonal. And theorem 6.7, so it says opposite angles. Let's read it here. Both pairs of opposite angles of a quadrilateral are congruent. A little hard to show, but so this one's not very practical for a coordinate proof, but we could use theorem 6.9. That the oops, hit the wrong button. And 610. So 6.9, to show that the diagonals bisect each other, you want to show that the midpoint, let me erase that, we are going to be showing that the midpoint is the same for both diagonals. Okay, so the midpoint's the same for both diagonals. Midpoint formula, you average your coordinates, so the midpoint of DB, 3 plus negative 3 is 0, and negative 2, excuse me, from B to D, so 2 and a negative 2 divided in half is 0. So the midpoint of this segment is 0, 0, and the midpoint of that segment from A to C, negative 1 plus 1, 0, divided by 2, 0. 2 plus negative 2 divided by 0, 0. So they have the same midpoint, so we can use theorem 6.9. We can also use the definition of parallelogram. And that says that your opposite sides are parallel, so I'd have to look at my slopes. I should have probably switched colors here, but so show opposite slopes are the same. Alright, so we're going to show that the slope of AD equals the slope of BC, excuse me, and the slope of AB equals slope of BC. Okay, so the slope of this line is 0, the slope of this line is 0. That shows that. And the slope of this line, rise over run, up 4 over 2. 4 over 2 is 2. Up 4 over 2, slope of that is 2. So by definition of parallelogram, since it's quadrilateral, it's a parallelogram by the definition. And lastly, you can use theorem 610 to show this. Switch back to green, and basically it's a combination. We already showed show slope and side congruent. So we already know the slope of BC is 2, the slope of AD is 2, and they both are equal length. They both have a length of square root of 20. So it's kind of combining the definition and theorem 6.6, but sticking to just one set of sides. Okay, so in your homework, they might ask you to use one of these theorems. We only needed to do one of these, but I showed it 4 different ways. You would just have to pick one of those ways, unless they said to use one specific way. A gate is braced as shown. How do you know that the opposite sides of the gate are congruent? So here's a gate, and I look at this and my diagonals are bisecting each other. So that's theorem 6.9, that if the diagonals bisect each other, it's a parallelogram. Doesn't say that this is a right angle. That would be nice to know, but we do know it's a parallelogram. There's your homework. Get to ask questions on that coordinate proof in class if you need it. So, see you then.